Argand diagrams and loci. Argand diagrams help us to visualize complex numbers. You can use them to understand relationships between numbers, to sketch loci, and to solve equations and inequalities. Let's start by thinking about what a complex number is. We can write a complex number in several different ways. If we write it in the form x plus iy, it consists of two parts: a real part, x, and an imaginary part, y, which is the coefficient of I, the square root of -1. An Argand diagram consists of real and imaginary axes, with equal scales on both axes. Let's plot the complex number z equals 1 plus the square root of 3i. It's just like plotting the point with coordinates 1 and the square root of 3 on the Cartesian grid. You could also plot the number as the position vector 1 over the square root of 3. There are other ways you can represent complex numbers using the modulus and the argument. Looking at the triangle in this Argand diagram, you can see that tan theta is the square root of 3, so the argument theta is pi over 3. By Pythagoras, you can work out the modulus, or magnitude of z, which is 2. So instead of plotting z using coordinates, you could use the modulus and argument to plot it in terms of distance and an angle. By convention, you generally give an argument between -pi and pi. It's helpful to plot complex numbers on an Argand diagram because this helps you understand the geometrical relationships between them. For example, if you plot z and w, you can immediately see that the complex conjugates are reflections of each other in the real axis. Adding and subtracting complex numbers works just like adding and subtracting vectors. Suppose you want to add z1 and z2. The sum of these two complex numbers is at the fourth vertex of this parallelogram. What difference does it make if you subtract instead? Similarly, when subtracting, you can visualize the result by drawing a different parallelogram. Let's look at the geometrical implications of multiplying a complex number by a scalar. Let's start with this complex number, z, and plot it on the Argand diagram. By multiplying z by 2, you can see that the real and imaginary components have doubled to give us 2z. On the Argand diagram, the distance from the origin has doubled, so the modulus has doubled, but the argument has stayed the same. Now if you divide z by 2, the modulus has halved, but the argument is still unchanged. Consider a complex number, w, whose modulus is 3. This statement means that w can lie at any point on the complex plane that is 3 units from the origin. You can describe this as a locus of points that are equidistant from the origin, in this case a circle of radius 3 centered at the origin. So this equation describes a circle of radius 3 at the origin. Suppose you want to show the region where the modulus of z is less than 3 rather than exactly 3. What difference would that make to the diagram? You can imagine z in any position where its distance from the origin is less than 3. So in this case, the locus of points is the shaded area inside the circle. Because the modulus of z cannot be equal to 3, you are not including the circle itself. You show it as a dotted line. You'll extend the idea of the locus as a circle by considering this equation. This tells you that the distance between z and 1 must be equal to 2. 1 is the point 1, 0 on the real axis. The distance is always 2, so your circle has a radius of 2. This time, the circle is centered on 1 and 0, not the origin. You will know that this will intersect the real axis at -1 and 3, because these two units are both 2 units away from 1 and 0. Let's imagine that a circle is translated from the origin in 2 dimensions, not just along one of the axis. How can you find its center? Consider this inequality. It states that the distance between z and some point is less or equal to 3, so that point must be the center of the circle. How can you find the point? If you rewrite the left-hand side as the difference between z and another complex number, you can see that the center must be 1 minus 2i. So, on the Argand diagram, you can plot the point 1 and minus 2. You're interested in all points within a circle of radius 3, this time including the circle itself. When you sketch this locus, you will need to think carefully about whether the circle will overlap the real or imaginary axis. What happens if there is a modulus statement on both sides of the equation? Is the locus still a circle? Let's start with this equation. As before, you can rewrite the statement to help work out what to plot on the Argand diagram, so you know that the 2 points you're interested in are 3 and 0 and 1 and 1. The equation you started with tells you that the distance between z and 3 is the same as the distance between z and 1 plus I. This means that the set of points z lies on a line that is equidistant from the points 3 and 0 and 1 and 1. It's the perpendicular bisector of a line joining these 2 points, since the bisector will always be equidistant from those 2 points. So far, we've looked at loci that are defined in terms of distance or modulus, but loci can be defined in terms of an angle or the argument instead. Suppose that the argument of z is pi by 3. This tells us that any complex number, z, must lie on a line that starts at the origin and makes an angle of pi by 3 with the real axis. This is called a half-line because it doesn't extend beyond the origin. If it did, the argument would be minus 2 pi by 3 instead. Let's consider this statement. As with the circles you've looked at, you will need to rewrite it as the difference between z and another complex number, in this case, minus 3 plus 2i. So you can plot the point minus 3 and 2 on the Argand diagram and add a horizontal dotted line to the right of the point. The argument is measured as pi by 4 anti-clockwise. This illustrates that the locus is a half-line starting at the point minus 3 and 2 at an angle of pi over 4 to the horizontal. Now let's think about how you could sketch inequalities for loci defined in terms of an argument. Again, you start by finding a point so that you can plot it on the Argand diagram. The point is minus 2 and minus 1. From the horizontal line starting at that point, you measure it at an angle of pi by 6. The inequality states that the argument must be less than pi by 6, so if you draw the half line as a dotted line, then shade the region between the 2 dotted lines. Now you're going to combine 2 different loci. You need to find the region that satisfies 2 inequalities at once. Let's take it step by step. As before, you can rewrite the statements as the difference between z and another complex number, in this case 2 plus I, so let's plot it on the Argand diagram. Looking at the format of the inequalities, you can see that the locus on the left is a circle, centre 2 and 1, while the locus on the right is a half-line starting at the point 2 and 1. For the circle, the inequality means you're interested in all points that are at least 1 unit from its centre, so this time you'll need the circle itself and the region outside it. For the half-line, you can add a horizontal dotted line to the right of the point 2 and 1 to show the argument. The inequality tells us that we need the region where the argument is more than pi by 6, but less than pi by 4. These should be dotted lines because they're not included in the region we need. Finally, you can shade the region that satisfies both statements. It's the region between these dotted lines and outside the circle. So you've looked at how Argand diagrams can be used to visualize complex numbers. Now you can use them to understand relationships between numbers, to sketch loci, and to solve equations and inequalities. Good luck!